So what can we do about malicious hardware manufacturers? So imagine that we're going to design a chip that's, say, for encrypting telephone conversations. And then we're going to outsource its manufacture to a fab, a company that builds integrated circuits. Well, if the fab is malicious, it can build a chip with a back door in it. And what that means is that maybe a third party will be able to listen to our conversations. Now, this is a serious problem. The US Department of Defense has a program for trustworthy manufacturing that uses onshore fabs, chains of custody, and even background checks and clearances. And if all that sounds like a pain, it's because it is. But as we saw in the exciting A2 work, fabs can insert malicious hardware, and then it's very hard to detect it. So what that means is that essentially trusted manufacturing is the only way to get strong guarantees. Still, trusted manufacturing is no panacea. For one, there are only 5 countries in the world that have advanced fabs onshore, and building a new one would take billions of dollars and years of R&D. So that means that, say, the government of India wants to build this encrypted chip at an onshore fab, they're going to have to use sort of early 90s vintage technology. And what that means is that they might be behind the cutting edge by up to 8 orders of magnitude if we take into account speed and area and energy consumption. So my co-authors and I looked at this and we said, how can we make this cheaper? How can we make trustworthy chips more cheaply? And it seemed to us like we would be able to use a probabilistic proof system to do so. So here's what I mean. So imagine that instead of designing a single chip that executes F, that's our computation, we're going to design 2 chips, one that we'll call a prover and then one that we'll call a verifier. And then we'll send those designs to 2 different fabs. The prover will go to an untrusted but very fast fab, and the verifier will go to a trusted but slower fab. And then once the 2 chips are built, they're going to be put together into a single device. And then that device is what we install into the system. So then when we want to run a computation, we send the verifier inside the device an input, and then it forwards that input to the prover, and it gets back a response plus a proof that the response was computed correctly. And then the verifier checks that and outputs the result. Now, this whole setup makes sense if the cost of the verifier plus the prover chip is less than it would have cost to just build F, our initial computation, in the trusted foundry to begin with. And there's reason to hope that this is the case. So theory tells us that at least asymptotically, the verifier should be able to save work compared to just executing the computation. And even though in these systems, the prover has massive overheads, as we saw with Cinderella a couple days ago, we hope that because the prover is built in this untrusted, extremely powerful fab, that can offset some of that overhead. Still, there are some challenges here. First, it's not enough to say that the running time is faster. We also need to worry about hardware things like energy and chip area. And we need to actually be able to build the circuit, which means we need a tight digital circuit design. And finally, the verifier needs to save work concretely, not just asymptotically, for problem sizes that we actually care about. So we sat down and we built this system that we call Zebra. And I'm happy to tell you that we've won. It's over. Trusted chips that's it, we've got them. No, that's a lie, I'm sorry. So really, we have a hardware design that sometimes saves costs compared to just building F in a trusted foundry. And for the rest of the talk, I'm going to tell you when we win and how, and when we don't. So Zebra is built on top of probabilistic proof systems. In these systems, the computation is expressed as an arithmetic circuit. And the arithmetic circuit is constructed such that its satisfiability is tantamount to correct execution of the computation. So what this means is that the prover's job is just to convince the verifier that there exists a satisfying assignment. Now, in terms of machinery for the prover to do so, there's kind of 2 strands in the system's work. One uses arguments, and these are systems like Zatar, Pinocchio, and Libsnark. Arguments are sort of computationally sound proofs. And the other uses interactive proofs, which are a kind of probabilistic cross-examination. And systems here are like Muggles and CMT and Allspice. Now, systems based on arguments have much more generality. This is because interactive proof-based systems sort of place restrictions on the arithmetic circuit. And in addition, because there's little or no interaction in the argument-based systems, they have much less communication cost than interactive proofs. So it seems like an obvious choice that we would just build Zebra on top of arguments. And we started to do that. And then we figured something out. It seemed like these argument protocols didn't really map very well to the kind of hardware that we would need to design. At the end of the talk, I'll tell you a little bit more about that, but right now I'll tell you how we found that interactive proofs did map to hardware and how we built that hardware. So Zebra builds on top of the interactive proof protocols from GKR, CMT, and Allspice. And so in these protocols, the arithmetic circuit needs to be layered. What that means is that the inputs go to a first set of gates, whose outputs go to a second set of gates, etc. This is an example of a layered arithmetic circuit. This is a single, double, and add step from elliptic curve point multiplication. And I want you to note that this is not the physical circuit that we would build in silicon. This is an abstract representation of the computation. So remember, what we said was that the verifier hands an input to the prover, and then the prover evaluates the arithmetic circuit and returns an output to the verifier. And now the verifier and the prover start to interact. So the verifier asks the prover some questions about the last layer of the circuit. And if the prover's answers are all consistent, then the verifier is convinced that the output was correct, just in case the prover was honest about the second last layer of the circuit. So now, how does the verifier learn that? Well, it engages the prover in another interaction, and that gives it a statement about the previous layer. So this continues until the verifier is holding a statement about the inputs to the circuit. Well, it knows those inputs, so now it can just check that, check the consistency. And if the prover was honest about all of this, then the verifier is convinced. Now, at each layer of the circuit, the verifier needs to ask a number of questions that's sort of logarithmic in the number of gates at that layer. So what we want is a circuit that's wide and not too deep so that the verifier can save work. So remember, we're building this in hardware, and so intuitively it seems like what we want is to parallelize this. And in particular, you might ask, well, look, we're executing these layers all at different times, so maybe we could just run them all at once. And unfortunately, that doesn't work. And the reason is the verifier needs to ask the prover questions in the right order, or else the prover can cheat. So in Zebra, we do something slightly different, and that is we pipeline the execution. Let me show you what I mean. So imagine that the verifier and the prover are interacting about the output layer of some computation. Now, at the same time, the prover can deliver a new result to the verifier. Now, once the verifier and prover are finished with that first computation, they move on to the second layer of the first computation, and now they can start to interact about the second computation's output layer. And the prover can deliver a third result. So you can see how this process could continue until the pipeline is full. And now the verifier and the prover are interacting about every layer of the circuit simultaneously, but they're doing so over different computations. And it only takes them the time of interaction for a single layer to complete a proof. So this is one example of the kind of design approaches that we took in Zebra. We extracted parallelism from the protocol. Another one of our approaches was to exploit locality. And what I mean by that is we wanted to avoid things like using RAM, because RAM is a bottleneck to the computation. So instead, remember, we're building custom hardware here. So we're not stuck with this sort of fetch, decode, execute model of a CPU. We were able to map the hardware to the flow of data through the computation. And in that way, we could avoid this kind of bottlenecks. And the final one of our high-level design approaches was to reduce, reuse, and recycle. What I mean is we reduced the amount of computation we needed to do by remembering previously computed results and then reusing them later. And we were able to recycle the same circuit to achieve different tasks during the computation. So these are kind of some circuit-level optimizations and observations that we had to make. And there were also some sort of system-level challenges. So one of those is, remember, this is an interactive protocol. So that means that the verifier and the prover talk a lot. And just building naively two chips and having them talk would be very costly. So instead, we say, well, we should use this technique called 3D integration, where we stack the two devices one on the other, and this reduces considerably the cost of that communication. The other limitation that I'll talk about is one that we inherit from the protocol itself, and that is that the verifier needs some help in the form of an input-independent pre-computation in order to save work. Now, in Zebra, we stipulate that we should build many chips at once and then share the pre-computations among them to amortize the cost of that pre-computation. These are a couple of the challenges at the architectural level. We talk about others in the paper. So now we've seen some of the circuit design stuff and we've seen some of the architectural challenges. Let's take a look at the evaluation. But first, what did we build? Well, we implemented a compiler that goes from a high-level description of an arithmetic circuit to synthesizable Verilog for a prover. And then we also designed two different verifier implementations, one for a hardware verifier in Verilog, and the other for a software verifier, say, running on a trusted CPU. That one's in C++. And then we wrote some sort of support software that helped with the pre-computations and made the simulations run faster. And then we started running simulations, and wow, this thing, it worked. It looked great. But remember, the point here wasn't just to make something that worked and generated a bunch of proofs. The point was to build something where the verifier plus the prover was cheaper than just building F in the trusted technology. And so that's our baseline. Imagine we have some computation. We're going to build in the trusted technology, or simulate in the trusted technology, the direct implementation of F, and compare that to the costs of the verifier and the prover. In terms of costs, what I mean is the energy that it takes to execute a computation, which sort of relates to the online costs of Zebra. In the paper, we also talk about chip size per unit throughput, which sort of maps to the manufacturing cost at a given performance level. Now, in terms of these measurements, the way that we did them is with circuit synthesis and simulation, with published chip designs, and with CMOS scaling models. And we were careful to account for sort of all of the costs that the verifier and the prover incurred during the computation. And then we imposed some practical constraints. We said the trusted fab needs to be 350 nanometers, and the untrusted fab should be 7 nanometers. And 350 nanometers is sort of 1997 technology, so think Pentium 2. 7 nanometers is, according to TSMC, who's sort of the biggest integrated circuit manufacturer in the world, this is a 2017, 2018 kind of technology. So what that means is that there's a 20-year gap between the trusted and the untrusted fab. In the paper, we also talk about other gaps and see how that affects the performance. And finally, we impose these sort of practical constraints. We say, well, the chip can't be too big, because otherwise we can't build it, and it can't dissipate too much power, because otherwise it just melts. All right, so what are our Fs? What do we actually build? Well, the first application is the number theoretic transform. This is a fast Fourier transform over a finite field. And it's used, for example, in computer algebra to, say, multiply huge integers or polynomials. So this graph shows us the ratio of the energy for the baseline to the energy that Zebra uses. So higher is better here. And what we see is that we kind of have two regions. One where Zebra wins for large computations, say above NTT size of a couple hundred, and one where we don't win for small computations. And this kind of makes sense because there's some overhead for participating in the protocol, and until the computation is large enough, the savings don't swamp out that overhead. So the second baseline is elliptic curve point multiplication over a curve 25519, which is a commonly used elliptic curve. And remember, point multiplication is sort of this primitive that's used for, say, ECDAH and ECDSA. OK, so again here we see a similar result, where there's a regime where the number of computations is too small, and there's a regime where the computation is big enough that Zebra saves. And here we see that's about for 100 or so parallel point multiplications. All right, so we've seen some performance stuff, and now it's time to go back to that pesky sometimes. So we started out looking for this way of replacing trusted fabs with something else, something cheaper. And the question is, like, did we get there? Are we there yet? Well, so Zebra applies in some kind of limited range. First of all, we need, as we saw, a wide gap between the technology of the prover and the technology of the verifier. And second, we have to amortize these pre-computations over many instances of Zebra. And the computation needs to be large in order for the verifier to save work. It needs to be efficient when expressed as an arithmetic circuit, which kind of rules out things like low-level bitwise operations. And it needs to be layered, shallow, and deterministic, which rules out things like RAM and complex control flow. So where do these restrictions come from? Well, the first 4 restrictions are common to essentially all built proof-based systems. So, for example, the need for a large gap between the prover and the verifier is essentially the same thing as saying, well, the prover has massive overheads when it executes these computations. And in terms of needing a very large computation to save work, well, a careful reading of the literature shows that even systems that only try to save work for the verifier have trouble breaking even unless the computations are essentially as large as the system can handle. But the last restriction that we need this layered, shallow, deterministic arithmetic circuit, that comes from the fact that we're using interactive proofs rather than argument systems. And so now we come back to this question. How was it that we didn't use an argument system like Zatar or Pinocchio or LibSnark? Well, we started out looking at those systems and we said, look, it seems like this should work, right? We should be able to parallelize all of these pieces of the computation in very nice ways. But remember, we had these other two design principles. We needed to exploit locality and we needed to reuse. And this is where we ran into trouble. So for example, in the interactive proofs, what we saw was that the prover needs to work one layer at a time. In these argument systems, the prover works over the entire arithmetic circuit at once, and that means that we lose locality. And in these argument systems, the prover needs to do a public key operation for every gate in the arithmetic circuit, and that means that we need these high-performance crypto primitives in order to get good performance. And that means that we can't share those circuits with other pieces of the computation. So while we did have parallelism, we didn't have locality or reuse, and this is what tripped us up. Now, I want to be clear here that I'm not claiming that this is a fundamental thing. These are just problems that we ran into and didn't see a good solution for. And we think that this is exciting future work. So let's recap. We described a new approach to building trustworthy hardware under this strong threat model. And we built essentially the first hardware implementation of a probabilistic proof system. But the system has some limitations. First, the improvements compared to the baseline are modest. And second, there's this limitation in terms of the applicability that we've just discussed. Still, we think that this is maybe a cool new approach for building trustworthy hardware. And we're hopeful that future work will make the verifiable ASICs model truly practical. With that, I'm happy to take any questions.
Fascinating. Oh, Matt Hicks, Michigan, A2 paper.
How's it going, man?
Yeah, I love this. I'm interested as well in dynamic verification of hardware. I think this is a fascinating take I didn't think of before, so it's great. Some kind of practical questions.
Sure.
So your one example seemed to be a purely combinational circuit. Do you see any challenges? What challenges would you expect if I introduce state, have a sequential circuit?
Right, so this is a good question. Now, remember, I think maybe I went through this a little quickly, but there's this restriction in the model using interactive proofs where RAM-based computations are kind of a sticky thing. So that's kind of an issue with the interactive proof-based approach. But I want to sort of back up for a second and make clear that, remember, when I showed that circuit, that's not the physical circuit. So inside the physical circuit, there is state, but the computation, the representation, needs to be unrolled into this arithmetic circuit with no state for all of these systems. This is a restriction of the system.
Okay. And also, you're heavily pipelining. You rely on pipelining to make things more efficient.
Yep.
So if you could imagine applying this to a Intel class processor that already has 20 stages of pipeline, and branch mispredicts are very expensive because you roll back everything, clear out the pipeline. Could you imagine clocking processors at 20 gigahertz to, get the same kind of throughput that we get from those processors, but being pipelined to match your verification system?
Yeah, that's a super fair question. I think what we saw is maybe the kinds of computations that we're really worrying about right now are a few orders of magnitude away in terms of complexity from something like a full processor. Now, in the literature, there's some very nice work on verifying the execution of processors. But in that model, the processor is even there like quite a, like a very stripped down kind of RISC processor. And yeah, so I think the high level answer is this is kind of a little far away from the ability to do something like a processor, where there are a lot of like low-level bitwise operations and sort of a lot of internal state for, as you said, branch prediction and this sort of thing.
Hi, Antoine Deligna from MSR. First of all, congratulations for your excellent work and well-deserved award.
Thank you very much.
I have one question. So your presentation got me thinking, since you're using an interactive system, to which extent do you think you could have a general purpose verification chip instead of having to build the custom-made chips for all kind of
Oh, so you're
programs you
asking,
want.
let me make sure I understand. The question is, could we use a general purpose verifier chip to work with different provers?
Yes, exactly.
Yeah, the answer to that is yes, there's no doubt. So in the paper, we talk about this a little bit. So the way that the particulars of the design that we have allow sort of for a change in the particulars of the computation, but not the shape of the computation. But even that's not a fundamental limitation. You could imagine building a verifier in such a way that it takes as sort of part of its input, here's the shape of the circuit, here's the pre-computations that go along with it, and yes, it can verify essentially any computation.